What's up, Sim Scientists, and welcome to a very special edition of Sim Science. Oh, it's not Sunday, it's Monday. Well, I'm sure you guys have been studying nonstop and extremely intensely for the final, as you should. It's chemistry. It's going to be tough, I'm sure, but you guys can do it. But for some strange reason, my inbox has not been inundated with requests for videos. So I'm just going to go ahead and go rogue here and make one on my own. And one thing we didn't touch on in review very much was water and a lot of things that go along with water. And I also think this is kind of, emotional and special because one of the very first videos I made, if I remember correctly, in December was about water. And I remember drawing these shapes and talking about it. So I'm looking in the notebook right now around page 70, 71, and 72, where we talked about different types of bond forces and different types and different attributes of water. You could have a class that goes on forever about water. Water is so special. So I'll use a nice water blue here as we talk about this stuff. So first of all, what kind of bond is this right here within the water molecule? Or I guess first of all, let's identify what we're looking at here. So what's the red? It's oxygen. And what's the gray? Hydrogen. Okay, so when we look at this bond within the water molecule, what kind of bond is it? Well, it's a covalent bond. Covalent. How do we know that? Well, it's between a nonmetal and a nonmetal. It's between hydrogen and oxygen, two nonmetals. If it were a bond between a nonmetal and a metal, then we'd be looking at an ionic bond. So it's a covalent bond. This is a covalent compound. Water is. And what kind of force is that? Is this covalent bond between hydrogen and oxygen right here? Is this a intramolecular force or an intermolecular force? It's an intramolecular force. Intramolecular. Why? Because it's within a molecule. Intra is within. Remember I said like introspection. Intra is within a molecule. So you have this covalent bond within a molecule between hydrogen and oxygen. Now, is this a polar or non-polar bond? And hopefully you said it was polar. Polar, these are both polar bonds, polar covalent bonds, which means this is a polar molecule. And what does that mean? What does it mean for something to be polar, or a covalent bond to be polar? Well, it means the electrons are shared unequally. So if you had a compound like oxygen gas, O2, where you have oxygen bonded together, just kidding. So if you had oxygen bound together, these electrons that they're sharing, covalent, sharing valence electrons. If you have the same atom, the electronegativities are the same. So they pull electrons equally. Make sure you review electronegativity in your periodic trends. If they pull the electrons equally, that means that they're shared equally, that there's going to be a divide between them that's equal, and it's non-polar. No one side has more electrons than the other. Here, though, are these atoms of oxygen and hydrogen sharing the electrons equally? No. Which one has a stronger electronegativity? Oxygen does. Oxygen does, because oxygen has a stronger nucleus. It has more protons in its nucleus, and it's going to pull electrons more toward itself. So we use our electron color here, and these electrons are getting pulled this way in this atom. Okay, so the oxygen pulls the electrons towards itself, and that creates two poles in this molecule. You have a negative charge up here because the electrons are getting pulled that way, and then these hydrogens have positive charges down here. So it's a polar molecule. What does that mean for water in terms of what it can dissolve? Well, if you forgot, like dissolves like. So something in terms of polarity can dissolve something else that has a similar polarity. So that means that water can dissolve other polar compounds. Okay, because the water molecule, each individual water molecule has these charges on it, it can connect with something that also has a positive charge, which can connect with a negative, and a negative charge, which can connect with a positive. So like dissolves like, water dissolves polar compounds. That means it dissolves polar covalent compounds, and it dissolves ionic compounds. Remember, ionic compounds are the most polar because in an ionic compound, you have a positive cation and a negative anion. And this compound is going to be held together because of these opposite charges. One gives up an electron and the other takes the electron, and they're held together. That's ionic. Okay, anyway, back to water. Water has polar covalent intramolecular bonds. So that's what's going on within water, and it can dissolve polar compounds. Now, what is happening between separate water molecules? Okay, so if this hydrogen again is positively charged and this oxygen is negatively charged, what happens when you have a positive and negative charge near each other? They attract. So you get this interaction between hydrogens and oxygens of different water molecules. And this is the key to the properties of water. So what do we call this? What do we call this right here? It's a hydrogen bond. Hydrogen bond. So hydrogen bonds exist between hydrogens and three elements. Do you remember what those elements are? Oxygen's one, obviously. Fluorine and nitrogen. These three. Noth. Or Fon. It's a lot of Fon. So if you look at your periodic table, you see the NOF are in the top right corner. They're the most electronegative atoms. So when you have the positively charged hydrogen and you have the very electronegative nitrogen, oxygen, or fluorine, it's going to be able to form a bond with that, which we call a hydrogen bond. Now, if you look at the chart on page 70 in your notebook, we talked about dipole-dipole forces, which are attractions between positive and negative. Hydrogen bonding is essentially the strongest dipole-dipole force because it exists between hydrogen, which, remember, hydrogen only has one proton and one electron, so when oxygen takes that electron away, hydrogen just becomes a proton on a stick. You get that positive charge that bonds with these three very electronegative atoms. So this is a hydrogen bond. And is that an intramolecular or intermolecular force? This time we're talking about an intermolecular force. Oops. Oh no, that's right. Molecular. Inter, between molecules. So we have two separate molecules here being attracted because of hydrogen bond. Okay, now this hydrogen bonding is what makes water what it is. So these, when you have, millions and billions and trillions of water molecules, and they're all forming these bonds. Okay, wherever they are, you're always going to get this type of bonding, and they start forming a lattice. Now, in the gaseous form, all these are broken. The heat that's put into the water breaks these, and all these water molecules go flying around as just water, or as just water molecules, as gas. In a liquid, you have these bonds kind of forming and breaking and reforming as they rotate and move around more. And then in the solid form, this is why water spreads out more in a solid form, which is rare. It gets dense, or it gets less dense in a solid form because they form these bonds and they become permanent and they spread out into the lattice structure, which you have drawn on page 72 in your chart. So this hydrogen bonding is what gives water its high boiling point. High boiling point. Okay, because it takes a lot of energy to break these hydrogen bonds completely and turn it into a gas. It also gives water its high surface tension. That's why there are bugs that can walk on water's surface, because the hydrogen bonds provide enough surface tension. Okay, so hydrogen bonding, it also gives it its high specific heat. So we talked about specific heat when we talked about enthalpy. It's how much energy you have to put in to raise something, 1 gram of something, 1 degree Celsius. So water stays cool, right? Even on a hot day, water is still cool relative to the air around it because it takes a lot of energy to heat up water. So the sidewalk or the bricks around a pool are really hot, but the water is cool, relatively speaking, because it takes a lot of energy to heat up water. All right, and that's because of the hydrogen bonding as well. So, like I said, I think at the beginning of this video, you could spend a lot of time talking about water and its unique properties and why those properties are so important. Our world would not work if water didn't have these properties. If water didn't get less dense when it froze, nothing on the world would work. Ice would sink. We wouldn't have our ice caps, which reflect the sun, and the earth would have been cooked a long time ago. Fish and sea life couldn't survive because ice would form and then sink down to the bottom and kill them all and crush them. All these types of things. Why the special properties of water are so important. So hopefully this served as something to help you review covalent bonds, maybe ionic bonds a little bit, polar covalent, non-polar covalent, intramolecular forces, intermolecular forces, and then the special properties of water, which are pretty much all due to hydrogen bonding. That's what makes water special. Keep that in mind. So make sure you look over that stuff on water, pages 70 through 73, and then 74 we talked about hydrogen bonding in proteins a little bit. Hydrogen with these three elements, nitrogen, oxygen, fluorine. But yeah, so that's pretty much it. Again, please email me if you have a topic you want me to make a video on or go over. Comment on this video with questions that you might have. Anything I can do to help you, I am happy to. Make sure you're going over the topics you missed on the practice exam and et cetera, et cetera. You guys are going to do great.